So last time we talked about operating systems from a very high level perspective. I gave a definition of what operating systems are from the perspective of this class. I've showed this picture where basically it said it's the software layer that sits between the hardware and the user application. It uses the physical machine interface and exposes a more convenient, easier to use virtual machine interface to the end user and to application. Okay, so we also did a quick history lesson that demonstrates the change of sort of the architecture of operating systems, the functionality, and their overall evolution with changes in hardware. Okay, so we'll pick up from where we left off, and I'm going to talk a little bit about OS functionality again. Okay, then what we'll do for the rest of the class is do a quick recap of architecture concepts that you should have at the back of your mind as we go along with this class. Okay, so I'm assuming some of those concepts you may have covered in 230. Okay, if not, then this will be the place where you will learn about the concepts. So, and if you have, then this is going to be a refresher. Okay, so with that architecture reminder, what we also want to do is understand why some of those features are actually in the hardware. And as we will see, there are operating system functions that that become easier because the hardware provides some support for them. Okay, so some of the features that you see in the hardware are actually motivated by what the OS needs to do, and we will see what are those features, why they are there, and so on. Again, as we go into depth, we will come back to all of these concepts and we'll look at those features in more detail. This is again only an overview, okay, just to give you some perspective on why some of the hardware features are there at all. Okay, so the last point is architectural support can either simplify, and if the support is missing, then it will complicate the design of operating systems. Okay, so a quick recap of OS functionality. I mentioned some of this last time already. What the OS does is a number of things, and so we have at the very top we have process and thread management. So users start applications on their machines. Applications are run as processes. The process may be multi-threaded if your application is multi-threaded. What the OS does is that it has to manage all of the processes and threads that are concurrently running on the machine. Okay? So from an OS design perspective, we need to think about what should the OS do to ensure that processes get their fair share of resources, hardware resources, that they run efficiently, their user sees a responsive machine, and so on and so forth. So that's basically, that brings you to concurrency, which is doing multiple things simultaneously. Okay, you may have computation and I/O overlapping. You may have multiple cores, so computation may be happening in parallel. There may be I/O devices that need to be managed. The OS is responsible for managing all of those devices. Okay? When we come back to the I/O section of the course, which is probably 10 to 12 lectures from now, we look at all of that in more detail. Okay? So I/O devices, how do you manage I/O devices? The big problem is I/O devices tend to be slow. CPU is very fast. Okay? How do you sort of bridge this mismatch? Okay? How do you have a fast CPU accessing very slow devices and not getting stalled at the same time? Okay? So that's something that the OS can help with. Okay? Memory management I talked about already. Your processes are resident in memory. The OS has to decide how much memory to allocate to each process or thread, how to vary that allocation dynamically as the needs of processes or threads change over time. Okay? Files and storage, okay, your data and data programs, applications, all of those reside on disk. Again, the OS is responsible for managing this disk. It does so by providing abstractions like files, directories, folders, subdirectories, and so on. Okay? And it has to manage the storage space. It has to decide how much to allocate to files. When you delete files, how to reclaim that space, and so on. Okay? So how are file systems designed? How do they allow you to manage disk space efficiently? Okay? Last point that we talked about was distributed systems and networks. Okay, so this is a networking part of the hardware that the OS has to manage. What abstraction do you provide to applications so that they can communicate over a network with other applications residing on other machines? Okay? That will be the very last component of the class. Okay, so we'll come back to all of this in more detail. This is just a recap of the functionality that the OS provides you. Okay. So this is a summary of what we talked about last time, or different perspectives of what an OS is. And you can think of OS as juggling uh, different resources on a machine, okay, and trying to allocate it to applications. You can think of it as the government that actually arbitrates between applications, provides fairness, fair policies, and so on, provides security and safety within your application, for your applications rather. Okay. You can think of an OS as a complex software system. Okay, so how do you design a very large scale software system? What principles apply? How do you make the right trade-offs? You can look at OS design from that perspective. And last but not least, you can think of OS as a history teacher. Okay, how has OS kernels, how have they evolved over time? What functions have been added? Why have they been added? And so on. These are different perspectives of what OS design can teach us, okay, for this class. Okay, so that's basically a recap of last time. Before I continue on with our architecture review, let me pause and see if there are questions here. Okay, this is actually chapter 1 of the book, okay, and there's some more material from chapter 1 that I'll talk about. Any questions? Okay, so we are going to start a review of computer architecture. Okay, so I'm going to just put up a picture of what you see inside your typical PC. Okay. This is a picture of a motherboard of a PC. Okay, lots of components. I'm not going to go into all of them, just point out a few. That's a schematic of this picture. So that's your CPU. Okay. These are slots that you actually plug in your RAM, main memory. That's where the RAM goes. This is actually the PCI bus. If you have PCI I/O devices, that's where they're going. At the very top, you have peripherals. Okay, those are all I/O devices. You may have your Ethernet card, you may have USB ports and whatnot. Okay. Many other things, like there's a battery in there to power the clock and so on and so forth. Okay. So just to give you a feel for what's inside a machine, this is a picture of what is inside a laptop. Okay. That's actually a desktop motherboard. So it's actually the same thing, except that when you open up any portable device, you'll see that most of what's in there is a big battery. Okay. This part is actually the motherboard. That's essentially this, and the rest of it is actually a battery. Okay. So most of what is inside your phone, tablet, or your laptop is actually a big battery, because you want long battery life, and the motherboard is actually quite small in comparison to the rest of what is in there. Okay. But that's just FYI. Okay, now what we want to go in and actually take a look at this picture and draw a schematic. Question? Or look at a schematic. Okay, so this is the same picture as the previous one, but with only the main components abstracted out. Okay, so basically, if you look inside a machine, there are 4 major pieces that we need to keep in mind, especially from an OS perspective. Okay, first is the CPU. Okay, you know what a CPU does? It actually performs the actual computation. Okay, CPU may have multiple cores. Okay. There may be multiple CPUs, each having multiple cores. Okay. Initially, from the perspective of this course, we are only going to think about a CPU as a uniprocessor, single processor, single core. Okay. Just to understand how do you design an operating system kernel from a very straightforward uniprocessor, single core perspective. But as we go along, we'll also ask the question, what would happen if you have multiple cores or multiple CPUs? What could you do better or differently? Okay. But if I don't say anything about multiple cores or anything like that, you have to assume that we are talking about a uniprocessor design, okay, the simplest possible design that you could think of from an OS standpoint. Okay. That's one major component of your machine. The other one is your main memory or RAM. Okay. This is where your data and programs are loaded that the CPU is executing. Okay, that's basically this box here. Okay. So CPU of the processor, RAM or main memory, and then you have I/O devices of various sort. There's a disk controller being shown here that's connected to disk. There's a USB controller connected to USB devices. There's a graphics adapter that's connected to a screen. Okay, it could be a built-in screen, or it could be an external monitor. There's a network card and so on. Okay. So those are all I/O devices. Now, one thing I will mention in the previous slide is you don't actually see the disk there, because the disk is a separate device that actually plugs into one of these buses if it's a certain kind of disk like a SATA disk or some such thing. Okay? And the thing that connects them all is your system bus. And that's basically the communication medium between the CPU, memory, and peripherals. Okay, you don't actually see the system bus on the previous slide either, but that's a key component that's going to connect all of these devices, allow them to communicate with one another. Okay? 4 key components: CPU, memory, I/O devices of various flavors, and the system bus. Okay, very straightforward. This is the picture you should have in mind. Okay, anything to clarify here? Okay, so now with that picture in mind, we are going to ask a few questions about what are the hardware features that you have in that previous box I showed you that are specifically meant for operating systems. Okay? So what are those features and why are they there? Okay, that's what we want to understand. So we are going to actually go a little deeper and look at very specific features, and we'll see what the OS uses them for or why they were put in there to make the job of the OS simpler. Okay? So basically in this column, there's a table where this column is the operating system service that are listed, and against each service you will see what are the hardware features that are there to better support the operating system to help it provide that service. The first one is protection, okay? And we'll see, we'll look at slides shortly. We'll see to enable protection, the hardware supports user kernel mode, it has protected instructions, it has base limit registers. Okay, but these don't mean anything, don't worry, I'll talk about that in just a moment. Okay, another OS service is interrupts. To support that better, you have interrupt vectors, your system calls, and your trap instructions and trap vectors to support them. You have I/O devices, or not I/O devices, I/O functionality. You have interrupts and memory mapping. The OS provides scheduling services, error recovery accounting. The hardware feature that's used to support it is a timer or a clock. Okay. Synchronization is atomic instructions. Virtual memory is TLB, okay, translation look aside buffers. Okay, now I don't know how many of these things you have actually encountered in 230. I'm assuming you've heard of some of these things. Yeah, if not, I'm going to provide a quick overview of it. But so let's start with each of those rows and dig a little deeper. We'll start with protection. Okay. So before I talk about protection, I'm going to mention something about the instruction set. Okay, you know that the CPU, any CPU, has a set of instructions it can execute. Those are the assembly instructions. Okay, that's the language that the CPU will speak. Okay, these are some examples of assembly instructions. Okay, that's a move instructions that move some data from a memory address into a register. Okay. This is an add instruction that adds the value that is stored in this register to the second register. Okay, these are all assembly instructions that you can use to execute your program. And there are there are lots of instructions. I just pulled out a few. Here are some that we will talk about in a little more detail. This is a move instruction that moves a control register. Okay. Here, the in or the ins instruction allows you to take an input string. Okay, that accepts inputs. It's a halt assembly instruction that will halt the machine, stop the machine. Okay. You have load task register, and there's a software interrupt instruction. So if you sort of execute that instruction, it will generate a software interrupt. Okay. There's a whole bunch of instructions. We don't need to worry about all of them. What is important from our perspective, OS perspective, is that all of these instructions can be partitioned into 2 groups. Okay. What we'll call regular instructions and protected or privileged / sensitive instructions. Okay. Regular instructions are those that any user program can execute. Okay. There could be load, store, add, move, subtract, whatever. All of those are regular instructions. Okay. And then there are the group of special instructions. Those are what we will call sensitive or privileged. Okay. Here's a small set of examples of what are actually special instructions on your machine. They are privileged or sensitive. Okay. Let's just take an example, a very simple one. Let's take the halt instruction. Okay. Now the claim is that these special instructions should not be executed by user programs. You should not let them execute that user program. Okay. And it's clear why, because if you let any arbitrary program just issue halt, the machine will stop. Okay. You cannot trust arbitrary programs to do things that may actually impact other programs or other applications on machine. So you can't really trust some application to just execute halt and then your machine stops. Right? So you want the OS to decide when to execute this instruction. So this group of instructions, only the OS kernel is trusted to execute, but not, we don't trust user applications to execute. Right? Because if the user applications were given control of this instruction, they could do arbitrarily malicious things. They could peek into the memory of other applications. They could arbitrarily stop the machine and do arbitrary things. They raise random interrupts and things like this. Right? So given any CPU, if you look at its instruction set, you can partition it into two groups. Okay? Regular instructions, sensitive, privileged. Sensitive and privileged instructions will only trust the kernel, because kernel is the only software entity that you want to trust. Okay? It knows what it's doing. Applications we assume may be buggy, they may be malicious, we don't actually trust them. Okay, so we need to ensure that these instructions can be only executed by application. Okay. Now, if that is the case, you have to ask the question, how does the operating system or the hardware ensure that user applications cannot execute this instruction? What is it to prevent them? I could write an assembly program that has halt, and I could compile it and start executing it. What prevents this program from actually triggering this instruction? What should we do to prevent it from executing? Yes. Can you speak up a little? User and kernel. So that's basically right. So you need something in the hardware to enable this support. Okay? So we will see what that, and this is where we get into protection. Okay? So what we want is some way by which the CPU knows whether the entity that's executing on the CPU is a kernel or a user program. Okay, and the simplest way to do this is have a status bit. Okay, there are multiple ways to do this. The simplest way is you are going to have a bit. If the bit is set, the CPU is going to assume that the kernel is running, okay, and then it will allow any instruction to be executed, regardless of whether it's a regular one or a special one. And if the bit is not set, the CPU or the hardware will assume that the user program is running, and it will explicitly prevent any user program from executing one of the special instructions. If you try to execute a special instruction when that bit is not set, the program will basically, there will be a trap and the program will be terminated. This is hardware protection feature. Okay, so this bit allows the CPU to execute either in kernel mode or user mode. In kernel mode, if that bit is set, okay, any program, any instruction rather can execute. Okay, the CPU will not stop any instruction from being executed. But if the bit is not set, you are in user mode. Okay? So assume that only user applications run, and user application can only execute regular instructions. And if you try to execute some of the special instruction, the hardware, because the bit is not set, will prevent the user program from doing this. Okay? That's a hardware feature that's in place precisely for this reason, because we only allow the OS to do certain things. In particular, we do not allow applications to directly do I/O. Okay? We do not allow applications to muck around with memory state, like page tables and so on. Okay? We do not let the user application actually change the mode bit. You cannot let a user application change the bit from kernel to user mode. That's also privileged. If you let the application switch it, then it could just switch it and start executing all the special instructions. So you don't let that. You don't let the application enable or disable interrupts or halt the machine. Okay? But the kernel can do all of those things. Okay? If you're in kernel mode, the kernel can do all of it. We trust the OS kernel, okay? But not user application. Okay. Now, what is shown in this picture is a generalization of the user and kernel mode. If you actually look at the Intel architecture, every CPU has to at least support a user and kernel mode, but the CPU can do more than that. So in the Intel architecture, you have what are called ring, and a ring level tells you what level of trust you have. Okay? In ring 0, okay, that's kernel mode. Everything goes. You can basically execute whatever you want. Ring 3 is pure user mode, only regular instruction. But there are varying levels of trust. There's ring 1 and ring 2. Those are intermediate levels of trust where you let some stuff more to execute, but not everything that the kernel can. Okay. For most practical purposes, you only need ring 0 and ring 3. You only need a user mode or kernel mode. But there are some special cases where you need intermediate levels of trust. Specifically, if you use virtualization on your machine, okay, the hypervisor will actually run. That's the thing that the virtualization software actually runs as the most trusted entity. Guest level operating systems run at ring level 1, and user applications within the guest run at ring 3. If you don't know what virtualization is, don't worry about this. Okay? So all you need to know really is there are at least need to be 2 levels of trust, full trust or no trust. But there are CPU architectures that will support different levels of trust. Okay, in Intel architecture, these are called protection rings. Okay, so you have this ring 0, ring 1, ring 2, and ring 3. Okay, yes.
So you need some way to switch between user and kernel mode.
Yes.
Like if you want to say shut down your computer.
Yes.
So how does that happen?
Okay, so how do you switch between user mode and kernel mode? There are multiple ways that can happen. Okay, if there is an interrupt or a trap, okay, basically hardware will automatically switch the mode to kernel mode and start executing the kernel. Okay? There are many things like that. There may be timers that go off. So if there are certain things that happen in the hardware will switch, and so I need to let the kernel figure out what to do, and it will switch the mode and let the kernel. That's the simplest way the mode will switch automatically for you. Okay. Any other questions here? Okay, so that's protection. Now, I said the user applications cannot do any of this. Only the kernel can do some of these things. Okay, but if you look at it, you will see that some of these things the user application may have to do indirectly. Okay? I/O is an example. I said we do not let applications do I/O. Okay? Only the OS kernel can do I/O. Okay, yet you have written programs where you can read a file, you can write a file, you can print and whatnot. Right? That is I/O. Your application is doing I/O. So you have to ask the question, if you do not trust your user programs to do I/O, yet you know that they do I/O, how does that happen? Okay, yes. Okay, you tell the kernel to do it. Okay, you don't trust the application to do it, but we trust the kernel. So we'll say, if you want to do this, you ask the OS to do it for you. Okay. So question is, how does that happen? The way this is going to happen is, if a user program or a process wants to do anything that is privileged, it has to ask the kernel. The way it asks the kernel, it invokes a special procedure or a function called the system call. Okay? A system call is, think of the system call as the API that the kernel has exported. That's the interface that the kernel has exported. That is how you communicate with the OS. That's how you tell the OS, do something for me. Okay? So whenever the user program wants to do anything that requires privileges that it does not have, it has to invoke a system call, and the system call will in turn invoke the kernel, and the kernel will do that operation for you. The kernel will check, is that the right thing for this process to do? It will do all of the right things for you. Okay? So this is basically why we have system calls at all. Yeah, so essentially it's a procedure that executes privileged instructions. Only the OS can execute it because they are by definition privileged, and this is how things work. This is a sort of control flow of how a process will do or invoke a system call. Okay? So essentially the executing process simply calls this function, which is a system call. Okay? The hardware recognizes that this is a special call, and that basically by invoking it you cause a trap. Okay? Think of a trap as an interrupt. I presume all of you at least know what an interrupt is. Yes? Okay. If you don't, this is the time to ask. Everything will make sense here. Okay, so you cause a trap. Okay, so trap is essentially an interrupt. The interrupt, what the interrupt does, this is the trap here. The interrupt will essentially switch the mode to kernel mode, and it will suspend execution of this program or this process. Okay? And it will basically start running the kernel. At this point, the process that invoked the system call has been suspended, and the kernel takes over. Okay, now you are in kernel mode. And basically the kernel says this process wants to execute the system call. It actually has the code for that system call in the kernel. So it will execute that function for you. Okay, you can actually pass parameters and all that just as you pass them to a function. Okay, it will execute it, and then once it's done executing, it's going to return. And when it returns, it switches the mode back to user mode. And then that process which was suspended continues executing again. Okay, now it has the results of whatever operation it had asked the kernel to perform. And we're done. Okay. So now you have to keep some stuff in mind. When you basically suspend the execution of this process, you have to save the state of that process, because when you resume executing, you have to begin executing exactly where you left off. So as far as the user program is concerned, it doesn't actually see that anything else happened. It resumes executing rather where it left off previously. So whenever you suspend the execution of any process, you have to save the state of that process. That includes the program counter, its register, all of that has to be saved somewhere. So the kernel is going to use all of those registers and so on. And when you resume execution, you have to restore all of them. Yeah, this process is called a context switch. We will come back to context switches a little later in this course. Okay, yes, question. Okay, why is the mode bit different in user mode and kernel mode? Mode bit is what tells the hardware, the CPU, whether you are running in user mode or kernel mode and whether you can execute all the instructions. So when you switch to the kernel, you have to switch to kernel mode. The mode bit 0 essentially tells the CPU it's kernel mode. Okay? This is simply an indication to tell what mode you are in. Any other questions? Okay, so that's system calls. We'll again return back to system call. This was simply to show you how protection works. Okay, here are examples of system calls. Okay, there are many of them. Several hundred system calls that any kernel will support. This is just a simple example. So these are some system calls that you can invoke to manage processes on your machine. Okay? Can you invoke the fork system call, for instance, to create a new process? This is how you start up a new process. When you start an application, something is doing fork, it starts up a new process, the process starts executing and so on. Okay? And then exit will actually exit a process. This is how a process terminates itself. Okay? There are system calls to do file management. Okay? You can open a file, close a file, read from a file, write from a file, and so on. Okay? Notice that I said these are system calls, okay? Because file I/O is I/O. It's privileged. Okay? Although you may have written applications where you read and write files, okay? Technically what's happening underneath is something is calling the system, or rather something is invoking a system call that tells the kernel to perform that operation for you. Okay? Your user program cannot directly read files. So that's an I/O operation, privileged operation. So you have to tell the OS, go read this file for you. So whenever you do any I/O, whether if it's file I/O, there is some system call that you have to invoke and ask the OS to do it for you. Okay, so all file operations privileged. Okay, so you will see that there is a whole bunch of system calls just for file management. There are a lot more. I'm not going to go into a lot of details, but just to show you that there are similar system calls regardless of the platform. Here is a table that shows you multiple columns. This column shows you system calls that Unix supports, any flavor of Unix, whether it's BSD, Linux, doesn't matter. These are the system calls that you have here. These are the equivalent system calls in the Windows world. These are Win32 calls. Yeah, they're also system calls, but on the Windows platform, this is just an explanation of what that is. Okay, I'll just talk about one here. So if you look at the very top, I talked about fork. This is how you create processes in the Unix world. If you want to do the same thing in the Windows world, you call an equivalent system call, which is create process. I'll create a process for you. It does the same thing that fork would do. Okay. So the API that Windows would expose to its applications are clearly different from what Linux or BSD or some of these other Unix-like kernels would expose. Yeah, but nevertheless, they do equivalent things. Okay, so that is protection, system calls, and whatnot. Now we'll talk about memory protection. Okay, so here's the picture to keep in mind. This is your RAM. Okay, and you have RAM. You have several things resident in RAM at any given time. Okay, so you have your OS kernel that's resident because it's clearly running, or not running, but it's executing. Okay, and then you may have multiple processes. I just call them jobs here. Okay, these are all the applications that are presently executing on your machine. And so they are essentially also loaded in memory. So another protection feature that you have to implement is you cannot let one application access or touch the memory that belongs to another application. Right? You cannot let a process modify kernel memory. That would be bad. If you can go and corrupt the kernel. You cannot let a process go and muck around with some other process's memory. That would also be bad. And if you have a browser and you are logged into online banking, just to give you an example, some of the state of your online banking is resident in the browser's memory. You let some other process access it, and if that's a malicious process or virus, now you're just given access to sensitive information. Okay, so you shouldn't let this happen. Each process can manage memory that's allocated to it, do whatever it wants with its own memory, but you shouldn't let it access someone else's memory. This is the basic protection feature. Okay? Now the OS has to enforce it, but it needs hardware support. Okay? So the question is, how do you prevent some process from accessing some other process's memory? But what you could do is you could just invoke an assembly instruction and stick somebody else's memory address. Right? You can just specify whatever memory address you want in an assembly instruction, and if you just say load, it will load, try to load at least that region of memory. And if that region of memory belongs to another process, then you shouldn't let that happen, okay, from a protection standpoint. How do you prevent this from happening? Any thoughts on this? Yes. You have to speak up. I cannot. Okay, so first thing is that the kernel, all of these instruction memory accesses have to somehow go through the kernel. That's sort of true, not quite, because if every time you access memory, you have to invoke the kernel, that's going to impose a huge overhead. Okay, so what we will do is we'll let the kernel outsource that to the hardware. Okay, so every instruction has to be, every memory access has to be checked. That part is true. Okay, because you have to check, are you allowed to access this region of memory or not? Okay? But we won't let the kernel do it. That's going to be far too slow. We'll let the hardware do it for us because that will be fast. Okay, so what you're going to do is simply check every time you access memory, saying, does this address belong to you or someone else? If it belongs to someone else, then you deny. If it belongs to that process, then you allow. Okay? The simplest way, there are many ways to do this, and we look at all of them later. Here's the simplest way to do it, is you are going to do a range check. Okay? This makes certain simplification. First simplification is, we'll assume that this process is contiguously loaded in memory. This is process A, this is process B, this is process C. This is how we'll assume processes are laid out in memory. If they're contiguously laid out, then all you need to do is whenever process 2 here tries to access memory, we'll see does it lie between these two address ranges. If so, you're fine. If not, you deny. Yes? That's the concept. You're going to check every time you access memory, you are going to say what is the region of memory that you allocate. Let's say it's address 100 to 200. Okay? So all memory addresses that process generates has to lie between that range because that's the region of memory you allocate. If you try to access address 300, you're going to deny, saying you only can access 100 to 200. Okay? The way you will do this, you have two special registers. Now this is where the hardware comes in. Okay, they are called base and limit registers. Okay? The base register stores the starting address of the process. The limit register stores the ending address of the process. Okay? Every time you basically try to access any region of memory, any instruction that accesses any region of memory, you check that memory address against the values in the base and the limit, and you compare. In hardware, you are going to do this comparison, and if the address lies in between, you are going to let that instruction execute. If not, you are going to raise a trap saying illegal memory access and terminate the process. Okay? Is that clear? People are not convinced. Yes, question.
So is that happening in kernel mode?
Is that happening in kernel mode? That's not happening in kernel mode, but it is happening in the hardware transparently to the process. So you don't actually have direct access to what's happening. Okay. You just execute the instruction, the hardware will check for you. So you don't actually perform this check. It's not a software check. It's a hardware check. Okay, you don't need kernel mode for this. Okay, you do need kernel mode to load the base and limit register. But once the kernel loads it for you, you can't modify it, you can't touch it. Something else is going to do the check, the hardware. Okay, yes, question.
What if you have like a process that only needs a little bit of RAM space to begin with, and then needs a bunch more later? How do you manage that with if it's restricted between the base and the limit?
So that's a good question. The question is what happens if the process grows over time? Okay, you allocate a new object. Okay, you instantiate new object, you need more memory. Process size grows. Okay, if you actually have what I've shown here, where this process is loaded here, there's a process that starts right where this process ends, it has no room to grow at all. Okay, then how does that work? Okay, we will come back to memory management later. Okay, because what I showed you is a highly simplified picture where I said processes are contiguously loaded in memory. Okay, and by doing so, you will basically have problem unless you left some gap here for this process to grow. But then you could say, how much gap should I leave? How do I know whether this process will need 10 megabytes of RAM, 10 bytes of RAM, or 100 megabytes of RAM? You cannot predict. Okay? So you basically need more sophisticated schemes than this gross simplification I've shown you. But all I wanted to point out here is hardware needs to do some checks to make sure any memory address is valid. Okay? Whether you have this trivial memory management scheme or something very sophisticated, that check has to happen. The check gets vastly more complicated as we relax the assumption that processes are continuous. The answer to the question is processes really are not continuous. You will have part of the process here, part of the process somewhere else, and so on. Okay, how to do that we'll look at when we come to memory management. Okay, any other questions? Yes. Yes, a move instruction would actually check anything that has a memory operand. Right, so there are many instructions that would have memory operands. So here is a move one that has a memory address. This address is going to be automatically checked by hardware, for instance. Right? So any instruction that has a memory address embedded in it will automatically trigger this check. It's done for the hardware by you. You don't have to do anything. Okay. So it is indeed an example of the one where this check has to happen. Any other questions? Okay, so this should now start giving you a flavor of why certain hardware features are there at all. Right? Let's take an example and say you had a very trivial CPU that did not support a base and limit register. Okay. So what would happen then? Yes.
Some programs might start like writing it to memory of another program, and then you'll have to go back to that other program and try to use that.
Okay, so basically if you don't have base and limit register, then do this check, you may corrupt other processes. You have something else to say. Okay. So either now there are no checks and hence you are basically giving processes free reign. Okay, there will be complete anarchy because you can go and do whatever you want in any region of memory. You can even corrupt the kernel if you want. That's number one. Or you will have to design a vastly more complex OS. What would then have to happen every time any process tries to execute any instruction with a memory operand, you would actually have to trap to the OS, and the OS would have to actually perform this check in software saying, should I let that instruction execute or not? Okay. So there are only two things. If there's no protection, you say that I trust everything, and then if something goes wrong, that's too bad. Okay. Or I actually do more work and perform this check in software because the hardware is not doing it for me. Okay, the way you do it in software is every time you execute any instruction, you have to invoke the OS. The OS has to do this check. And then it has to flag it as yes or no. Okay. Now you can imagine that is going to impose a substantial overhead. To execute one assembly instruction, if I have to invoke the OS and run 10 instructions to do that check, that's a huge overhead. You'll get like orders of magnitude slowed down. You'll have a very slow machine. Or you basically say, I don't do the checks, I let applications have free reign and soon application will start crashing just because somebody had a bug and something went wrong. So you will see that by putting in some simple hardware features, you have made the life of the OS much simpler. Because to provide the same protection in software would have been a tremendous overhead and cause a significant slowdown. They should give you some indication of why certain hardware features are there. They make the job of the OS much easier. They make the hardware much easier to run and so on. Okay. So here's another picture of a process. So I showed a simplified version of a process which is just a blob of memory here. But if you actually peek inside the process, this is the logical layout of any process. Okay, process basically is a region of memory. It has sub-regions that are referred to as segments. Okay, segments have certain purpose associated to them. There's something called a text segment, or also referred to as the code segment. This is where the code of your application resides. Any code that you write is compiled or interpreted, is converted into machine code or assembly instruction. That is what is in the text segment. Okay. There are two others, there are many different segments, but for the purposes right now, we'll only look at three. Okay. Text segment, heap segment, and data, text segment, stack, and data slash heap. Okay. You must have heard of a stack. Okay. Stack is where when you invoke a function, it pushes its arguments onto the stack and so on. And when the function returns, you pop those arguments and the return values. So the stack is where you store variables and so on. The heap or the data segment is where you dynamically allocate memory. You run malloc, new, run constructor, instantiate object. This is where you put this dynamically allocated memory. Text segment doesn't change typically. Okay, once you return code, that's the code that's loaded. Okay. So typically when you have a process, it will at least have three segments. Okay, the code segment where the code resides, and the other two segments are quote unquote data segments where you will have the stack and the heap. Okay. These two segments are dynamic, they grow and shrink. Depending on when you invoke functions, your stack will keep growing. When the function returns, the stack will shrink. Just when you allocate memory, the heap will grow. When you deallocate memory, the heap will shrink. So these two segments are by definition dynamic. Stack segment is static, it doesn't change. So the code doesn't change when it's executing, it's already been written. Okay. So these are the segments we'll keep in mind. We'll come back to this later. I'll tell you why I said all of this. Yeah, because we want to look at a little more hardware details and try to understand what happens as far as memory management is concerned. Okay, so if you now look at, let me start with a different picture here. Okay, if you look at the typical memory that you have on a machine, there's not one quote unquote memory, but there are different things that can serve as memory. Right? So you have on the one hand registers. Okay, these are very fast regions of memory, very small but very fast. Yeah. And then you could have, at the other end, you have RAM. Okay, that's your main memory. Between the registers and RAM lie your caches. You may have L1 cache, then L2 cache, and then L3 cache. Okay. These caches store data and or instructions that have been recently executed. Okay. So that if you re-execute them again, you don't have to fetch them from main memory. They are faster pieces of memory. So you can directly fetch them from the cache, thereby giving your execution of your program a boost. Otherwise, you will basically have stalls where you are going to go fetch that instruction and or data from main memory again. Okay, so as you go up the memory hierarchy, your speed increases, okay? But cost also increases. Faster memory costs more. So typically on a machine, you are going to have less and less of the faster and faster portions of memory. Right? So you will have less L2 cache in terms of size than RAM, and less L1 than L2, and then you will of course have only few tens of registers at most. Is that clear? This is a typical memory hierarchy on a machine. At the very bottom, you have disk. Okay, disk can also act as a backup for RAM. It is where you have persistent storage. Okay, so this is what is referred to as a memory hierarchy on a machine. Okay, speed goes up as you go up the hierarchy. Cost also goes up, so sizes go down. Now, as far as the OS is concerned, user programs are concerned, etc., typically they only manage registers and or RAM. Okay? L1 and L2 caches are typically handled by hardware. Okay? You don't explicitly say put this in an L1 cache and so on. The hardware manages it for you. Okay, so as far as OS is concerned, we will assume these are present, but you don't explicitly have to manage them. You only have to deal with registers and RAM. You have to figure out what goes into the register. The compiler can do that for you and so on. Okay, so let me come back here. So now I introduce what registers are. So they are basically one-word pieces of memory, very fast, managed by, accessed by the CPU. Okay, so there are many or different ones. There are general purpose registers where you can store any variable or data. And there are some special registers, and I am assuming you at least heard of some of them. There is one called the program counter, the instruction pointer. Know what it is?
Keeps track of the current instruction that you're on in your program.
Okay, that's good. So program counter, very key register. Okay, you have basically in your code segment, let me back up here. Okay, that's your code segment, that's where your code resides. How do you know what is the next instruction to execute? You meaning the CPU, how does that know? The way it does it, it has a special register that's going to point to what it's executing now. Okay. And then basically the next instruction is the one after it. You're going to sequentially execute unless your branches and so on. But just assume that you start with the first instruction, you execute the second instruction and so on. So there is a register that is going to point to what you want to execute. That's called a program counter. There are registers such as the stack pointer and the frame pointer that tell you where the stack begins and where the stack ends and so on and so forth. Okay. So these are all special registers that you don't want an application to directly modify. The OS modifies them. Okay, the hardware modifies them. Okay. General purpose registers up to the user process. It can store whatever it wants in that register. Typically the compiler may decide. And these variables are accessed frequently, so rather than keeping them in main memory, let's put them in a register. So you have very fast access to it. Okay. Now the more important thing on the purposes of this class is when you switch from one process to another. Okay. Each process is going to have its own set of registers. So to prevent the registers from the previous process from getting overwritten when you switch, you have to save the state of the current register somewhere. And you have to load the state of the new registers for the new process. Okay. So every time you switch from one process to another, or you switch from the process to the kernel, when you do a system call, you take all the registers for that process, you store them somewhere. Typically you store them in main memory or kernel memory. Kernel will say, here is all the registers for this process, I'm going to save them here, then I'm going to load some other processes registers and let it execute next. Yeah, because registers are state of that process. You have to save the state so that when you resume execution subsequently, you can reload those registers so the process is where it left off previously. Okay, is that clear? So you always have to, when you switch between processes, save current registers and load new registers for whatever you want to execute next. Okay, this process is referred to as a context switch. We are going to look at all the details of how this is done when we do process management. But our real interest here is to understand how registers are managed by the OS. They have to be saved and restored every time a process is suspended and resumed. Okay. So caches I already mentioned, you have multiple levels of caches. They are typically not maintained directly by the OS. You don't actually save the cache state and restore cache state. You just let the hardware deal with it for you. So one process may actually override the cache state of another process. So when the old process starts executing again, it may start with a partly cold cache, and it may have some cache misses as a result. Okay, this is simply because some of its cache state got overwritten. Simply, and OS doesn't manage the cache. So this is a price you pay because you don't explicitly manage caches. Okay. That's not true for registers. You don't go override. You actually save and restore. Caches, you don't do that. You let the hardware deal with it. Okay, so now we are going to talk about traps. Okay, so we are done with memory. So we are switching to the next of those protection things, and this one is traps. Okay, so traps are similar to interrupts. If you know what an interrupt is, very similar concept. So think of them as special conditions that are detected by hardware that generates an interrupt for you. Okay. So if you have, let's say, if you do divide by 0, if you write a program does divide by 0, your program is going to basically terminate. Okay, because it's illegal to divide by 0, the hardware is going to throw a fault. So you're trying to do something that's not possible to do, and then you basically have a problem. Similarly, if you try to read, you generate a memory address that tries to read a memory location that doesn't lie between the base and limit registers, that's illegal memory access. You're going to raise a trap saying this program is doing something it shouldn't be doing. And there are many other things. If you invoke a system call, that's also going to be a special condition that signals to the OS something has to be done. Okay? So traps are special conditions that are detected by the architecture, and the OS has to handle them. So the OS, basically think of them as exceptions. So if you know what in Java world, traps are essentially like exceptions. Okay, so something happens, your exception is thrown, you go into a routine that will handle that exception. Same is true here. When a trap is generated, you have to go into a special routine that is going to handle that trap. And so that typically that routine resides in the OS. So what is going to happen is when some process generates a trap, you are going to essentially first you are going to save the state of that process, all the registers are saved. You basically switch to kernel mode. Okay. OS is going to start executing, and then you are going to go to the trap handler. Okay. That's the function that is going to handle that trap or exception. For every trap that you can generate, you need to have a trap handler. Just as when you have an exception in Java, you write a routine or some piece of code, not necessarily a routine, but a piece of code to handle that exception. Okay. Same is true, same concept is true here. Okay. So these are hardware traps, so you have to have trap handlers. Okay. Now the way it is actually simplified for you is traps in hardware are numbered. Okay. So you have trap 0, trap 1, trap 2, trap 3 and so on. Okay. And then what the OS is simply going to do is it is basically in hardware is going to load a table that looks like this. So basically for every trap 0, 1, 2, 3, there is a memory address. Okay. The memory address basically is the address of the function that is going to handle that trap. It's the trap handler's address. Okay. So the way the hardware is going to work is when you trigger a trap, okay, you don't actually trigger a trap, you trigger a trap with the ID saying this is trap 7. So then you will basically save the state of the process. You're going to look at this trap vector. This is referred to as a trap vector. It's simply a table that allows you to index. And if it's trap 7, you're going to look at this 8th entry here. Okay. And then say what is the address of the trap handler. And then you're simply going to jump to that address and start executing the trap handler, okay, in kernel mode. Once you're done, then you are going to basically resume execution or terminate the process if it did something. Okay, is that clear? So it's sort of like a system call where so the system calls are also trap actually. It's a type of a trap. So a system call is a special trap where you're going to do exactly this. The trap handler is essentially the code for the system call in this case. Yes, there was a question there.
You just actually answered it.
Okay. Yeah, so this is the hardware mechanism that allows you to implement not only system calls, but it's a more general mechanism that any special condition that requires OS to intervene. Okay, and you think of it as any exception. Okay, in your Java program, your program itself handles the exception. But in this case, the exceptions are raised by user processes that are handled by the kernel. Okay? Any questions on traps? I think I have one more slide here, which essentially says the same thing. Okay, so I actually have some labels here which say this is the system call, or these are essentially from the OS perspective, they're just numbers, but from the OS's perspective, they also mean something. So you have illegal address, memory violation, illegal instruction, system call, there are a whole bunch of them. Okay. The hardware feature that supports them is this trap vector, because you can quickly index from the trap ID and figure out where to go to handle that trap. Okay, so trap vectors are the hardware features that enable the OS to efficiently deal with them. Okay. So basically remember one more thing is this is simply a performance optimization. Just as I said, what would have happened if there are no base and limit registers? You can ask what would have happened if there was no trap vector. Okay, you could still handle traps. You would have to do extra work to figure out what happened, or you would have to, in some case, basically you put in more code to say what kind of a trap it is and then hardwire the trap address in the code so it jumps, rather than having a general table that you can simply index it. Okay, so you have to basically put all of this functionality in software. It's a little less efficient, but can be done. Okay, so those are traps. The next hardware feature is I/O control. Okay, there are 2 or 3 more left, so we're going to pick up pace here, go through them quickly. Okay, so I/O control. So this is basically what hardware features you have to enable you to do I/O, or you as in the OS to handle I/O. Okay. So the thing to keep in mind, we'll come back to I/O devices later. So this is sort of a very quick overview of how I/O is done. And we'll look at this more detail later. So the way to think about this is take any I/O device. And you can think of that I/O device as having a small microcontroller on it. Okay? So you can issue commands to that I/O device saying, go do something. Okay? So you can, for instance, tell the graphics card saying, go display something on the screen. You can tell the disk, go and read this piece of data from disk, or go write this piece of data. You can tell your Ethernet card saying, send this network packet out. Okay. Okay, so for every I/O device, there are a set of commands that you can issue to it. Okay. Basically, the typical commands are go read data from your device or write data to that device, but there may be many others. Okay, because it's an input-output device, so input and output are clearly the two commands you always have to support. Okay. The way it typically works is there's a tiny processor or a microcontroller on the device itself. Okay. The CPU essentially issues a command to the device. The processor on the device then executes that command for you. Okay. This is how typically I/O is going to happen. Depending on how sophisticated that microcontroller or processor is, you will have either very dumb I/O devices that do very little other than read and write bytes, to very sophisticated devices. Like the graphics card has actually, if you buy very sophisticated ones, they may have more cores than the CPU itself. Okay, they are fairly sophisticated in what they can do. Okay, they have their own instruction sets and so on and so forth. Okay, so there's a whole spectrum of I/O devices, but what's common is they all have a microcontroller or a processor that can accept commands from the CPU, and they will do the I/O that you ask them to do. The CPU issues commands and continues. So what would then happen is, because I/O devices are slow, the CPU is not going to issue a command and sit and wait. Okay, you don't tell the disk, read this chunk of data and then wait there while it performs that operation, because the disk is very slow. What you typically do is you will just issue the command and then you'll continue execution. You may start doing something else. Okay. When the I/O device has actually finished execution of the command, okay, it is actually going to raise an interrupt, equivalent to a trap. Okay, tell the CPU saying, I'm done. I finished whatever you asked me to do. Okay. That interrupt will cause whatever process was executing to be suspended. You will go back to the kernel. The kernel will then go and look, saying what command was issued, what are the results. It will accept the results from the I/O device, and then that I/O will complete. Okay, you may actually hand those results back to the application. For instance, you are doing a file read. Okay, you will issue that command to the disk. Once the disk has finished, the OS will get the results on the disk and then hand those results back to the application. Okay, this is how most I/O works. Now there are what I just described to you is referred to as asynchronous I/O. Okay, there are many different ways I/O is actually handled. Okay. So what is shown in this picture are two such mechanisms. One is referred to as synchronous I/O. That one is asynchronous. Next slide I'll talk about memory mapped I/O. Okay, so this is the user process. Okay. There is a device driver. That's the piece of the code in the kernel that talks to the device. You must have heard of device drivers. Okay. There's an interrupt handler that deals with the device driver, and then there is the I/O device itself. Okay. All I/O requests, this is how they're going to flow. They're going to come from the process into the device driver, which is really the kernel. Okay. The kernel, then you basically talk to the hardware, and then the results are going to come back when the device is done. Okay. Now, if your process that issued that I/O device is going to wait for its results to come back, okay, so you say, I read a file, okay, and then you are going to wait, okay, or read some input from the keyboard, you are going to wait. That is referred to as synchronous I/O. Synchronous means blocking. You are going to block until the I/O instruction or I/O command completes. This is one mode of doing I/O. And now you can imagine what asynchronous means. It's non-blocking I/O. You issue an I/O request, but the process does not block. Okay, process continues execution. Okay? So the I/O request is actually being handled by the hardware, but the process here is not blocked. And later on, when the results come, okay, the OS is going to issue exception, not an exception, is really going to do a signal to the process saying your I/O request is complete. And then you can get the results back. And I'm assuming that most of the code that you've written, okay, so far has all been synchronous, because that's the default mode of operation. But you could write applications that do asynchronous I/O. that do not block, okay, that can continue to do something else while this I/O operation is going. Okay, if you want to write very efficient applications that have very high I/O throughput rates, typically those might use asynchronous modes of operation, okay, because that gives you some efficiency gains. Okay? Why that is the case, we will not go into. All that you need to know is either I/O can be blocking or non-blocking. Blocking is referred to synchronous, non-blocking is asynchronous. Okay. Now, the one thing I will mention is from the kernel's perspective, regardless of whether the process is blocked or not blocked, the kernel is definitely not going to block. Kernel, the C is going to issue the command and is going to continue. Okay, so regardless of the application, inside the kernel, once the I/O request arrives, everything is non-blocking. Kernel doesn't sit and wait for the disk to finish. It will just issue the command and start doing something else. That is something to keep in mind. Okay. Third mode of operation, memory mapped I/O. Yeah, memory mapped I/O is typically used when you need to do a lot of bulk I/O. You're not reading bytes, but you're reading megabytes or gigabytes. So if you actually say, give me 1 byte, and then you say, give me another byte, that's not a good way to read hundreds and thousands of bytes. You want to basically say, give me a lot of data all at once in one command. If you want to do all of this kind of stuff, you are going to use what is referred to as memory mapped I/O. I will not have a picture here. No. So what happens in memory mapped I/O is essentially you are going to issue a request to your I/O controller, okay, to the I/O device, and basically tell the I/O device saying, rather than in telling me that the I/O is done, get the results and put it in this region of memory. Okay? And then you let that device directly access memory. This is why it's referred to as I/O, memory mapped I/O. So here's a picture that I'm going to show just to illustrate the concept. This is your disk. Okay? This is RAM. Okay, let's suppose that the user has issued a request saying read a large file all at once. Okay? So what the OS will do is going to be clever. It's not going to start reading the file 1 byte at a time. That's going to be too slow. It's going to issue a request to the disk controller, okay, saying go read this entire file, and I'm going to give you a memory buffer, okay, that is allocated for you, and once you read it, just directly store all of the results in that buffer and then notify me. Okay. So now you're given this I/O controller direct access to memory. Typically, I/O controllers don't muck around with memory. They just read the results into a local register and then signal the OS saying your I/O operation is completed, go read it from that register. Here, you're basically given access to memory to that I/O device, and the I/O device is then going to just start doing direct reads or writes from memory. Okay, this is referred to as memory mapped I/O. Okay. So the CPU no longer has to be in the way between the I/O controller and reading that data into memory or writing data from memory into that I/O. You just issue a command and then you give a block of memory and data is either directly read or written to it. Okay, this is a more sophisticated way of doing memory, not memory, rather doing I/O, and it basically is also more efficient. So if you want to do bulk I/O, that's the way to go, assuming your I/O device supports memory mapped I/O. Okay, the controller has to support these kinds of commands, but most of the sophisticated ones will do that. Okay, yes, question.
In this case, what does PC stand for? PC is your virtual memory. The second bullet point.
Oh, yes, good question. I don't know. I think what it is saying is that you are going to reserve actual RAM, not virtual memory, and I haven't even introduced what virtual memory is. So I wouldn't worry about it. So it is just, don't worry about that. So you are basically going to do I/O directly to physical RAM, okay, not virtual memory, which I haven't even introduced. So it's pointless to talk about it right now. Any other questions? Okay. So here's a small set of steps that have to be executed in order to do, let's say in this case, asynchronous I/O. Okay, I'm just giving you all the steps that have to happen. I have explained most of those already, but here is just a way to take a look at what is going to happen. So let's suppose you want to now issue an I/O instruction. The CPU wants to issue an I/O instruction to some I/O device. You want to do this in an asynchronous way. What will happen is first there will be an interrupt. Okay, so you want to do I/O. You will save the state of the CPU. This is all the process state is saved. Okay. You are going to at this point disable interrupts. Okay. And I'll talk about why you are disabling interrupts in just a moment. Then what you are going to do is you'll go into the interrupt handler routine to do that I/O. Okay. You will then basically issue that command to the I/O device. Okay. Once you are done, you are going to restore software state, re-enable interrupts, and essentially continue execution of the process. Okay. Some low-level details, and we'll come back to all of this when you do I/O. The only thing I want to point out here, rather than go through all these details, is that you are doing something that's disabling interrupts and enabling interrupts. Okay. The reason this is done is when you are actually handling one interrupt, okay, you're handling one exception, you don't want another exception to come in and interrupt that exception. Okay, so when you're doing one exception handling, you are going to either queue up any other exceptions that are raised in the meantime, or you are going to ignore them. Okay, this is done simply for safety, because otherwise you are going to have recursion. Okay, you basically, the process raised a trap, you jumped into the interrupt handler routine. There's another trap in between, then you're going to jump into another interrupt handler routine, and then you may recurse and not know where to come back. So typically when you deal with exceptions, you do not take any other exceptions while you are doing that. So you say, I'm handling an exception, other exception either have to be wait or they may be ignored. Okay, sometimes when you disable interrupts may be queued and re-delivered, and sometimes they may be ignored depending on the hardware. Okay. So because the handling I/O devices requires you to raise a trap, the thing that you will have to do whenever you jump into any trap handler is the disabling and enabling of interrupts. Okay. This is another hardware feature that I had mentioned earlier that you need to handle I/O devices, which is enabling and disabling. And it should be clear why that is necessary. Yeah, because you don't want recursive traps which may cause problems. Okay, that's a simple reason. Yes, question. Yes, you do always have to save the state, because what traps will do by definition is they will typically user programs raise traps or some arbitrary external event raises traps. Right? So, but whenever a trap is raised, you have to suspend execution of that process and jump into the kernel. Okay? So when you suspend execution of that process, you have to save state, because then at some later point you will resume execution. Okay? So whenever there is a trap, by definition, you are going to always save state of whatever is running, and then jump into the trap. Okay, any questions? Okay, the two more hardware features and then we'll be done. Okay, so first one is very simple. That's there's a timer on every machine. Okay, that's part of the clock. Okay? Every machine typically has something called a real-time clock that keeps time. There is a clock inside the machine. It is going to keep time. Because there is a clock, you can also have what are called timers. Okay, you know what a timer does. You can set a timer for a certain period of time, and then that period of time has elapsed, then the timer is going to go off. Okay, your CPU or not CPU, machine also supports the same feature. Okay, and it's going to use the real-time clock to allow the timer to tick down to 0. Okay. So now you can ask what use is a timer on your machine? What can you do with a timer? Any thoughts on what you will do with a timer? Yes. Okay, you can do sleep. You must have done sleep, I assume. Okay, if you want to wait for a certain period of time, okay, you can say sleep for 10 seconds. How is that implemented? That has to be implemented with a timer. Okay, something will set a timer for that period of time, and you've done, then you'll basically be woken up or whatever. Okay, so user programs use it all the time to put in a certain amount of delay. Okay, so that's one use of a timer. There's another very important use of a timer from the OS's perspective. Yes?
Random numbers.
Okay, you want to do random numbers, you could do that as well. Okay, so now as I was saying, there are many users from a user perspective, but there's also, the kernel also needs timers. Okay, so what it will use timers for is CPU scheduling. Okay, something we haven't talked about so far. Okay. If you have multiple processes running on your machine, and you want to fairly allocate the CPU time to each machine, the way you are going to do this is a timer. You will say process A runs, and then you say it gets to run for 200 milliseconds, and you set a timer. When 200 milliseconds have elapsed, you will say now you are done for some time. I'm going to switch to another process. Okay, you are going to do a context switch to process B and say now process B gets to run for 200 milliseconds. Set another timer. And the timer goes off. You say now you're done. I'm going to switch to process C. Okay. This is how CPU scheduling works. This is how when there are multiple processes running concurrently, each gets its turn to run on the CPU. Okay. What is actually enabling that underneath is a timer. Okay. In this case, the kernel is going to set the timer. Okay. And when the timer goes off, that process is evicted from the CPU, something else gets to run. Okay. So that's basically the timer feature on your machine. There are also, okay, so what this thing is showing is what happens when the timer goes off. When the timer goes off, there's a trap. Okay, that's what this is showing. You go into the trap handler and say, this timer has elapsed, what should you do? There's a user process that I put asleep, you'll wake that process up. If this was the end of a context switch, you will basically run the CPU scheduling algorithm and pick another process to run. Okay, that's what the trap handler for the timer will do. Okay, so last concept here is synchronization. I presume that when you did some threading material in 230, you probably learned about synchronization some. Okay, you must have learned about locks or semaphores or monitors. Yes? Okay. So locks, semaphores, monitors all allow you to do what is referred to as synchronization. They allow multiple threads to coordinate or synchronize. Okay. From our perspective, we are going to ask what is it that the OS has to do to enable locks, semaphores, and monitors and so on. Now, this may not make complete sense now, but we are going to come back to it and look at it in a lot more detail. So what happens underneath, the way synchronization is implemented underneath are through special assembly instructions. Okay, there's an instruction that is referred to as test and set instruction. Okay. This instruction enables implementations of either a lock or a semaphore or monitor by the OS or your application runtime, like if it's Java or C or whatever, pthreads. Okay. So the only thing I'll mention here that you want to keep in mind is to implement synchronization, you need special instructions in the hardware. The one that we want to look at when we come to synchronization is what is referred to as a test and set instruction. This is also referred to as an atomic instruction. You can atomically check a value and set it both in a single clock cycle. But typically, you can check in one instruction and set in another instruction. Test and set can do both atomically in one single instruction. Okay, why that is necessary, I think, is too complicated to explain without the right background. So we'll have to wait or defer that discussion to when we talk about how to implement locks and so on. But the only thing I'll mention here is there needs to be hardware support for synchronization. Okay, so I'm going to end here. We're running out of time. So basically, what we have done here is done a quick refresher of computer architecture and looked at a lot of features, okay, that you need to keep in mind. Okay, so we will keep coming back to this feature. So if some of this was not clear to you, please go review what's in the OS textbook. If it's still not clear to you, come talk to me. I may refer you to some basic book on architecture that you can use to refresh you. So the assumption is you will know all of this material, at least have some familiarity. You don't have all of the details when we talk about whether it's processes or memory management and so on. Okay, so let's end it here today.